1661. Cambridge is swept by a revolution of ideas. Descartes rules the show with his mechanical universe without void, but Newton appears, and everything goes to hell. He boldly declares space is real and absolute, and God is its creator through his omnipresence. Scandal! His ideas attack every foundation. One spinning bucket will prove who's right. An era begins that will divide science into before and after. Part 1. The philosophical groundwork. Newton dived into Cambridge University in 1661, right in the middle of Europe's intellectual battles. At that time, Cartesianism was on the rise, shaking up old Aristotelian beliefs and new experimental methods. René Descartes promoted the idea that the physical world worked like a massive machine, following mechanical laws, and dismissed the possibility of interaction at a distance. He argued that matter only affected other matter through direct contact and viewed space as merely filled by bodies. In Descartes' world, there was no empty space, just matter swirling around in big vortices. Many people liked this idea because it cut out any mysterious forces in nature, but others were bothered by it, feeling it left little room for God, apart from kicking off the cosmic machine. Newton stumbled upon these arguments early on, and they had a massive impact on how he thought. He dove deep into Descartes' writings, but in the end, he pushed back against nearly all major Cartesian ideas. This wasn't just a minor disagreement, but a deep-seated clash extending to basic metaphysics. While Descartes saw matter as just space occupying, Newton argued that space existed on its own, independent of any matter. Newton believed absolute space was the backbone of his entire system, arguing that space wasn't just about relationships between objects, contrary to what Descartes believed. Instead, space existed independently, whether filled with matter or not. This was groundbreaking because it gave space an almost divine quality. Furthermore, Newton linked space with God's presence throughout the universe. In the General Scholium of the Principia's second edition, he asserted God's omnipresence, saying God's existence across all space essentially created space itself. This view startled followers of Descartes and Leibniz, who thought of God as outside the physical realm. For Newton, suggesting God existed outside of space was akin to denying God's existence altogether. Everything, including minds and souls, had to connect with space, otherwise it didn't exist. This view horrified some of his peers, who saw it as treating the divine in too physical manner. Newton also didn't agree with Descartes' idea of motion being purely relative to other nearby bodies. Descartes suggested that motion was just about changing positions with immediate neighbours, meaning there wasn't a definitive answer to whether something moved or stayed still. Everything depended on your viewpoint. Newton argued that this made physics unworkable without a stable basis for motion laws. He needed absolute motion and space for his dynamics to make sense, using his famous spinning bucket experiment to show that true rotation was different from simply seeming to rotate. When water climbs the sides of a spinning bucket, Newton pointed out, it showed real rotation relative to space. Yet Newton struggled with a major problem he couldn't solve completely. Absolute space and time can't be directly observed or measured in experiments. We only experience relative motions and positions among observable objects. Newton recognized this, noting that direct observation of absolute quantities was out of reach. His workaround was to use absolute space as a foundational concept, enabling physics to proceed. He proposed using measurements based on the theory to infer properties beyond direct observation. Real forces acting on a body distinguished true from apparent accelerations, ensuring that the true motion could only change through direct force. This created challenges that fueled philosophical debates for centuries. Although Newton claimed to derive his conclusions purely from experiments and phenomena, critics argued that he relied on metaphysical ideas beyond observation. This debate became widely known through his clash with Gottfried Leibniz, who developed the contrasting idea of relationalism, where space was merely the relationship between physical objects. Time is all about the sequence of events involving different objects. According to Leibniz, the idea of absolute space didn't make sense and contradicted the principle of sufficient reason. In a well-known exchange of letters between 1715 and 1716, Samuel Clarke defended Newton against Leibniz's ideas. Their argument touched on physics, metaphysics, and theology, with neither one budging. Both realized that key questions about God's connection to creation were in play. This wasn't just abstract philosophy. It was about profound truth regarding divine intervention. Newton thought God played an active role in keeping the universe in order. He didn't agree with Leibniz's idea that God made a flawless world needing no further divine tweaking. For Newton, proofs of God's guidance were everywhere in the universe, demanding constant divine involvement. The balance of the solar system and the setup of planet orbits hinted at careful, ongoing guidance. This theological aspect couldn't be separated from Newton's approach to natural philosophy, even if later interpretations tried to downplay it. In the General Scholium, Newton wrapped up by stating that discussing God based on observable phenomena was natural philosophy's true mission. This wasn't a side note, but showed his deep belief that physics and theology were intertwined. Whether he was calculating the paths of planets or delving into biblical prophecies, he was engaging in theology. Part 2. The Methodology Revolution. Newton honed his method over years of intense intellectual battles. His first big paper, in 1672 on light and colour, immediately stirred up controversy. People like Robert Hooke and Christian Huygens criticised both his experiments and his ideas. Feeling deeply misunderstood, Newton developed a lifelong distaste for public disputes. These clashes pushed him to set down fundamental rules for how science should advance. He wanted to separate solid knowledge from mere guesswork or theory. This led to what scholars now call his epistemic triad. He sorted ideas into three categories: verified theories, speculative hypotheses, and queries. The last category includes ideas that aren't certain, but provide a way to reach solid conclusions. Hypotheses can help during investigations, but aren't claimed as proven truths. Newton used them as starting points for reasoning, but never as conclusions from observations. His method evolved significantly between the first edition of Principia in 1687 and later ones. The first version of Book the Third had 9 hypotheses. By 1713, in the second edition, Newton restructured everything, keeping only 2 hypotheses and rebranding the others as either rules of reasoning or phenomena, based on their role in logic. Newton's most straightforward statement of methodology was his 4 rules of reasoning. Rule 1 advocates accepting causes that are both sufficient and true to explain phenomena. This echoes Newton's take on Occam's razor: nothing more when less works. Rule 2 explains that similar natural effects should be linked to the same causes whenever possible. For example, the fall of a stone in Europe and America, as well as breathing in both humans and animals, share causes. This allows us to draw universal laws from specific experiments. Rule 3 states that if a quality is found in all bodies we can test. Like being solid, it's a universal trait. This led to treating gravity as a universal property, even though Newton had tested only earthly and observable celestial bodies. Rule 4, the most debated and philosophically deep, asserts that conclusions drawn by induction from phenomena should be seen as accurately true until new evidence challenges them. This rule champions experiment over speculation, grounding knowledge even when certainty is out of reach. Newton believed we could attain knowledge useful for practice and theory, and potential hypotheticals shouldn't undermine conclusions based on evidence. In the second edition, Newton included the General Scholium, which contained his famous methodological statement. He wrote, "Hypotheses non fingo," a Latin phrase that translates to "I frame no hypotheses," or "I feign no hypotheses." This led to centuries of scholarly debate due to its ambiguity. Newton clarified that anything not derived from phenomena is a hypothesis, and such hypotheses are unwelcome in experimental philosophy, whether metaphysical, physical, or based on mysterious qualities. In experimental philosophy, specific propositions arise from phenomena and expand to general truths through induction. This marked Newton's way of setting his method apart from rationalist systems like those of Descartes and Leibniz, who offered mechanical explanations for gravity. Leibniz came up with the idea of whirlpools or vortices, imaginary fluids swirling around planets to explain how they move. Newton thought this was just making stuff up that wasn't needed based on actual observations. He'd already laid out the mathematical law of gravity, which worked just fine for explaining how things move in space. But some people criticised Newton too, saying he made stuff up by saying things could act at a distance. How could one object influence another across empty space without something in between to do the job? This to them was bringing back mystical qualities that the mechanical philosophy had supposedly gotten rid of. Thinkers like Leibniz from the continent found it offensive to their philosophical sensibilities, even if it worked mathematically. Newton fired back by saying he had shown that gravity is real and it follows precise math laws. Whether this gravity worked through unknown ways or just directly through space was still up for debate, though privately he did think there might be some sort of mechanism, going so far as to toy with ideas like ethers. He never put any of these theories into his published work as established truths based on what we see. This way of going about things marked a big shift in what counted as real science. Before, scientists wanted to identify the causes and mechanisms behind everything. Newton figured just describing how things work mathematically was enough knowledge. You didn't need to understand why gravity follows the inverse square law to use that law successfully. This idea of knowing how versus knowing why became a big part of the philosophy of science later on. Newton showed that having exact math laws that describe what we see is a big deal in science. Asking for mechanical explanations or deeper causes might be jumping the gun before fully examining things. Better to get solid math descriptions down first, instead of piling on unsupported theories. Still, Newton didn't stop looking for deeper explanations or physical causes. His work on optics ended with a bunch of questions about the nature of light, matter, and force. These weren't final answers but ideas to explore further. He suggested things like subtle fluids and active principles that could potentially explain what we observe. This whole balancing act between two extremes was something Newton managed his whole career. On one side, pure empiricism risked drowning in data without any real understanding. On the other, pure rationalism threatened to create beautiful theories that had no basis in reality or testing. Newton's approach mixed careful math with reasoning shaped by what we observed. It took some serious math skills to deal with the messy realities of actual observations. In the Principia, he used fancy geometry to draw conclusions from ideal scenarios and then explain the differences between theory and what we actually see. He kept tweaking the models to better fit reality, a method that became common in mathematical physics. You start simple, covering the essential parts and then slowly add complexity to get a more accurate picture. Newton showed this method in how he developed celestial mechanics in the Principia. His method also involved what we now call error analysis and understanding uncertainty. Newton knew that measurements have mistakes and only give rough approximations. He worked out ways to draw solid conclusions from less than perfect data. Recognizing that certainty has different levels marked a mature take on how empirical science works. Newton's rules for reasoning shaped scientific methods for 2 centuries after he passed. They influenced how scientists made inductive inferences and drew conclusions beyond just the observed cases. David Hume's critical take on causation and induction targeted Newton's approach, and Immanuel Kant developed his transcendental philosophy, partly to figure out how Newton's science achieved such comprehensive knowledge. The phrase hypothesis non fingo turned into a sort of battle cry for those who supported an empiricist view of science. Thinkers from the 1800s, known as positivists, often looked up to Newton as their guiding figure, completely dismissing anything that smacked of metaphysical musing. It was pretty ironic. considering Newton himself was secretly devoted to some metaphysical, theological, and even alchemical pursuits. The polished image of Newton that emerged during the Enlightenment didn't match up much with who he really was. Part 3. The Hidden Theology. Isaac Newton wasn't your typical thinker when it came to religious beliefs. Throughout his life he hid the fact that he didn't agree with the Church's official stance on the Trinity. Newton saw the traditional view of the Trinity as a big distortion of what Christianity was meant to be. He believed this misinterpretation started in the 4th century after the Council of Nicaea in 325 AD. Newton didn't just look into science and math, he also delved deeply into theology. He wrote millions of words on biblical prophecy, analysed old texts, and tracked how Christian ideas changed over time. He was thorough and precise, applying the same critical techniques to religious texts as he did to his scientific work. Although he shared a manuscript with John Locke questioning the Trinity's biblical foundation, it was never published. Newton knew his views would be seen as heretical, and in 17th century England, such beliefs could ruin a career and pose serious risks. Professors at Cambridge were supposed to be ordained in the Church of England, which posed a dilemma for Newton in 1675. He couldn't honestly swear to beliefs he found incorrect. With the help of Isaac Barrow, his predecessor, he got an exemption from ordination requirements. This experience taught Newton to keep his thoughts on theology private. He practiced what scholars call Nicodemism, outwardly conforming while holding different beliefs inside. Newton was consistent in attending church and publicly upheld Anglican beliefs when necessary, but he did so to keep his career and work safe. He was convinced that God was one, not a trinity, and saw Jesus as God's Son and the Messiah, but not as equal to God. This outlook made him an Arian, similar to Arius, the early theologian whose teachings were condemned at Nicaea. According to Newton, the Father alone is the true God with ultimate power. Newton merged scripture analysis with philosophical thought to challenge the Trinity. He couldn't find solid scriptural backing for it in original texts, as many passages were later additions. For example, the Johannine comma in 1 John wasn't in early manuscripts. He also argued that the Trinity was logically flawed. How could 3 distinct persons be one and the same substance? The notion that the Father sends the Son, yet is equally eternal, seemed more like human error than divine mystery. Early Christians, Newton believed, worshipped a singular God, influenced by Greek philosophy over time, not by Hebrew monotheism. Leaders like Athanasius, he argued, pushed this idea through politics and textual changes, a view he detailed in a comprehensive manuscript critiquing Athanasius. Newton's approach to theology was closely tied to his views on physics. His belief in God's complete unity mirrored his theories of absolute space and time. Just as God is one, space and time are whole and indivisible. The idea of mixing up relative and absolute notions in physics echoed misconceptions about God. Newton thought God's omnipresence literally shaped space, with space and time being ways God exists, blending spirituality with science. This belief system underpinned his physics, where he saw God's hands guiding the universe's workings. Occasionally, God had to tweak things to keep the universe stable, like the solar system. Gravity might be more about God's direct influence, rather than just some mechanical force. This idea was quite different from what many Enlightenment deists believed. Deists thought of God as a creator who made the universe, but then let it run on its own, like a perfect machine. Newton found that idea both theologically and scientifically flawed. To him, the evidence pointed towards God continuously governing the universe, not a mere machine running on its own. Newton was also into something called prisca theologia, or ancient theology. He thought God had shown true religion to Noah and the patriarchs before Moses. This original religion was simple. Worship the one true God and follow 2 moral rules. Love God fully and love your neighbour as yourself. In Newton's view, All ancient peoples initially shared this pure religion. Over time, priesthoods in places like Egypt, Babylon, and Greece had ended up with only corrupted pieces of this original revelation. Pythagoras, during his travels, learned real wisdom and passed it on to his followers in a symbolic way. He believed ancient temples were actually models of the heliocentric universe and expressed deep cosmological truths. For Newton, this idea allowed him to think of his work as reviving ancient wisdom, not coming up with brand new discoveries. The heliocentric system, nature's mathematical laws, and proper worship of God were all part of a single unified view. He thought modern philosophy had fallen from its ancient greatness, and he aimed to bring back that lost knowledge. Newton's interest in alchemy was partly about uncovering ancient wisdom hidden in symbols. He thought alchemical texts might hold truths about matter and forces, wrapped in allegory. The philosopher's stone could be both a real substance and a metaphor for deeper understanding. This wasn't just mysticism, but a thoughtful way to study ancient sources. He worked on biblical chronology to pin down accurate dates for ancient events, using astronomical calculations. He decoded references to astronomical events in ancient writings to rebuild a true timeline, blending his astronomical skills with textual research for better theological insight. For Newton, these pursuits weren't separate. They were all part of one big investigation. He also studied biblical prophecy to understand God's plan for human history. Books like Daniel and Revelation, in his view, contained encrypted messages about the past and future. He developed complex methods to connect prophetic symbols with real historical events, concluding that the corruption of the Trinity would last until the end times. Based on his calculations, he thought the true religion wouldn't be restored until around 2060, thanks to a timeline that began with Charlemagne's crowning in 800 as Holy Roman Emperor. Newton saw himself as living in the times of long-predicted religious decline. His work in theology was as passionate and focused as his scientific studies, not just hobbies he dabbled in. Science and theology competed for his attention, both aiming to understand God's nature and reveal divine truth. After Newton died, there was a big question about what to do with his theological writings. Publishing them could make him look like a heretic and hurt his reputation. Hiding them would mean concealing a major part of what drove him. Ultimately, they chose to keep them secret until the 20th century. When people finally learned about Newton's theological beliefs, they didn't quite know how to make sense of it. How could the founding father of modern science hold such seemingly irrational religious beliefs? This showed how modern views often assume science and religion should be separate and even opposed. For Newton, though, they were all part of one seamless journey to discover truth about God and creation. Part 4. The Optical Battles. Back in 1666, when he was still a student, Newton got his hands on his first glass prism. He dove into light and colour experiments that would flip the world of optics upside down. These groundbreaking findings stirred up arguments that lasted for years. The constant back and forth shaped how Newton approached science and intellectual sparring. At the time, people thought that white light was pure, while colours were seen as distortions. According to this view, when light hit glass, the glass messed up the pure white light, creating colours. This meant the colours seen through prisms were from the glass damaging the light, suggesting that more glass would further corrupt it. Newton blew this belief out of the water with his simple experiments. He let white sunlight pass through one prism, splitting it into a rainbow of colours. Then he used a second prism in a clever way to mix those colours back into white light with no loss whatsoever. This showed that colours weren't distortions of white light. They were actually its basic components. White light was a mix of different coloured rays that travelled together. The prism didn't alter the light, but merely separated what was already there. Each colour had a unique way of bending when passing through glass. Newton deduced that light's different forms correlate with different colours. Red and blue light, for instance, weren't the same. They refracted differently through materials. Every colour had its specific angle of refraction when moving from air to glass, and the spectrum visualized this range for the white light's components. Newton shared these insights in a major write-up for the Royal Society in 1672, which he called Letter, containing his new theory about light and colours. Newton argued his work provided concrete proof, not just wild guesses. He believed the results were obvious when viewed through geometric evidence from experiments. Robert Hooke, England's top authority on optics, immediately took issue with Newton's theory. Jealous of the challenge from the younger scientist, he proposed several objections and alternatives. Hooke believed that Newton's proposal leaned on the idea of light being particles or corpuscles, while Hooke himself thought light travelled as waves. This put Newton's theory in his crosshairs. Newton was incensed because he thought Hooke missed the point entirely. Newton emphasized that his discoveries didn't rely on theorizing about whether light was particle-based or wave-like. The experimental findings around refrangibility spoke for themselves. Christian Huygens critiqued Newton's results too, although in a calm and less confrontational manner than Hooke. Leveraging earlier work, Huygens crafted an advanced wave theory of light, explaining both reflection and refraction. According to him, as each part of a wavefront moved forward, it created new wavelets spreading out like ripples. The particle versus wave debate lingered on for over 200 years, with Newton leading the particle theory charge and Hooke and Huygens holding the wave theory banner. Each idea grasped some concepts easily, while tripping over others. Newton's particle model elegantly accounted for phenomena like straight-line movement and distinct shadows. He argued that if light were waves, it should bend around obstacles, similar to sound. Sounds could appear around corners, but lights couldn't escape obstruction, suggesting a straight-line path was more particle-like than wave-like. Later observations of light bending through tiny slits challenged this view. Newton's corpuscular theory saw reflection as particles bouncing elastically off smooth surfaces. Different sizes or shapes of particles could explain varying colours, as they would each refract differently. As for refraction, Newton imagined that particles sped up when hitting denser materials, causing them to bend toward the normal. This theory meant light needed to move faster in denser materials, but it turned out later that wasn't true. Newton did recognise some things begged for wave-like explanations, though. Things like soap bubble surfaces show colourful interference patterns based on their thickness. Light either bounces back or goes through the same thin film without clear changes in the situation. So, Newton suggested that these little light particles, or corpuscles, had phases that made them either reflect or pass through. According to him, these corpuscles might create waves in the ether as they travel, which could catch up and cause these alternating phases. This theory was kind of a combo, trying to keep the particle idea but adding wave concepts. It showed how Newton was open to updating his ideas when the evidence demanded it. Optics, which came out in 1704, was Newton's big work on light. Unlike the dense math-heavy Principia, it was in English, making it easier for people to understand. The book described experiments that readers could try themselves and carefully drew conclusions from them. It also included long questions, inviting further investigation. This way, Newton speculated more freely than he could in Principia. He wondered if the light particles might be different sizes for different colours. He also thought varying densities in an ether might clarify optical phenomena. These weren't final answers, just ideas to explore. The optics had a unique impact on science, different from Principia, despite being less mathematical. It served as a model for blending observation with theoretical thinking in experiments. Newton's questions showed how to guide research without clinging to rigid beliefs. David Hume even used this approach as a template for his philosophy. The feud with Hooke deeply affected Newton, making him shy away from intellectual disputes and delay publishing some works. He only allowed Optics to be published in 1704 after Hooke's demise. This tendency to avoid controversy meant many of his thoughts remained unpublished for years. In 1801, Thomas Young's double-slit experiment strongly backed wave theory. When light passes through two slits, it creates a pattern of light and dark bands on a screen, something straight-travelling particles couldn't explain. More tests in the 1800s supported wave theory, with findings on interference, diffraction, and polarization. Even though Jean-Baptiste Biot initially tried to explain polarization with particles, more evidence leaned toward waves. By the end of the 19th century, the wave theory mostly replaced Newton's particle idea. But then quantum mechanics showed that both concepts were partly right about light's dual behavior. The photoelectric effect found in the early 1900s unexpectedly brought back particle ideas. Light knocks electrons off metal in ways wave theory didn't fit. Einstein suggested light is made of energy packets or photons. With this, light showed both particle and wave traits, depending on the test situation. Modern physics accepts this wave-particle duality as key to quantum mechanics. Light acts like waves in interference and diffraction tests, but like particles in the photoelectric effect and Compton scattering. Traditional waves and particles both fall short of fully explaining quantum stuff. Even though incomplete, Newton's particle theory guessed aspects of today's photon ideas. His thought that light had discrete entities moving in space caught part of the truth. The old debate between Newton and Huygens couldn't be settled by classical physics. They were both right and wrong in ways they never imagined. Part 5. Explores the Principia and Universal Mathematics, the groundbreaking work that redefined science. Published in 1687, The Mathematical Principles of Natural Philosophy is arguably the most impactful scientific manuscript ever. Newton developed a mathematical framework that linked earthly mechanics to celestial ones through universal laws. He demonstrated that the force causing apples to tumble is the same one making planets orbit the sun. This breakthrough was an immense intellectual leap forward, changing how we approach natural philosophy. This work's roots trace back to exchanges with Robert Hooke around 1679 to 1680. Hooke theorized that planetary movement results from two forces, one that keeps the planet moving tangentially by inertia, and another that pulls it toward the sun. The combined effect of these forces, governed by precise mathematical laws, creates orbits. Hooke also suggested that the central force diminishes with the inverse square of the distance from the sun. This inverse square law was something Christopher Wren and Edmund Halley were also considering. However, neither Hooke, Wren, nor Halley could derive Kepler's observed laws of planetary motion using this concept. They lacked the mathematical tools and insights for such a derivation. Newton, on the other hand, had worked out much of this math years before but never shared it. In 1684, Halley visited Newton and inquired about the inverse square forces linked to elliptical orbits. Newton quickly confirmed the connection and said he had calculated this previously. Although he couldn't locate his old papers, he promised to redo the demonstration. This interaction spurred Newton's most intense creative phase, leading to the Principia in less than 2 years. The project grew beyond its initial scope to cover a vast mathematical exploration of motion. Book 1 establishes general theorems about motion under central forces through geometric methods. Book 2 delves into motion through resisting media and challenges Cartesian vortex theories. Book 3 applies the mathematical framework to our solar system, deriving planetary movements from observed data. This accomplishment was revolutionary, uniting abstract math with real celestial phenomena. Newton detailed how to deduce the existence and form of universal gravitation from Kepler's laws. He even predicted refinements to Kepler's models due to gravitational interactions among planets. Principia begins by defining core concepts like mass, momentum, and force, assigning precise mathematical meanings to terms that were previously vague. The well-known scholium on absolute space and time follows, establishing Newton's metaphysical groundwork. Then come the three laws of motion, which underpin all arguments that follow. Newton's first law, stating that objects maintain their state of rest or uniform motion unless acted upon, wasn't his original idea, but built on Descartes and Galileo. Nonetheless, Newton made it fundamental and gave it a clear mathematical expression. The principle of inertia clarifies why planets continue moving without needing constant force. The second law states that a change in motion is proportional to the force applied and occurs in the force's direction. This became the essential link between force and acceleration, now written in physics as force equals mass times acceleration. Newton described it geometrically, using momentum changes over infinitesimal time periods. The third law, entirely Newton's own, posits that every action has an equal and opposite reaction. When one body exerts force on another, the second body applies an equal force back on the first. This law proved vital for understanding complex systems, ensuring internal forces in a system balance out to maintain total momentum. Building on these principles, Newton used geometric methods to derive multiple theorems. He demonstrated that an inverse square central force leads to elliptical orbits with the force's centre at one focus. He also showed how the period of an orbit corresponds to its distance, aligning perfectly with Kepler's third law. These findings didn't just vindicate Kepler's observations, they rooted them in fundamental principles. Book 3, called The System of the World, brought these abstract mathematical ideas to bear on real astronomical phenomena. Newton started with 6 phenomena, outlining the patterns seen in planetary and lunar movements. So Newton used his reasoning skills to figure out universal gravitation from the patterns he saw. His argument was a mix of solid math and a close look at real-world limits. He proved the moon's centripetal force equals Earth's surface gravity. After working out the force needed to keep the moon in orbit, he found it matched Earth's gravity, linking the forces on Earth and in space. The old idea of earthly and heavenly forces being different crumbled away. Newton then showed that planets and their moons follow the same inverse square law, with Jupiter's and Saturn's satellites plus the Sun's planets all lining up with the math. This pointed to one force, filling all of space and guiding everything in the cosmos. Newton called this gravitation, linking it to the masses involved. His equation said that the force is the product of two masses divided by the square of the distance between them. With this, he moved from vague explanations of planetary movement to a precise law. Each bit of matter pulls on every other bit with this math-based law. The big takeaway was the idea of one basic force behind everything we observe physically. Newton liked to start with simple models and add layers of complexity. First, he nailed down how two bodies move with just gravity between them, then threw in other factors like extra bodies and uneven mass shapes. Every step brought his math closer to what actually happens. He even figured out how the sun changes the moon's path and explained the wobble in Earth's axis with tidal forces. He pointed out how Jupiter and Saturn slightly change each other's paths with gravity. These tweaks let him make exact predictions from the messiness of the real world. In the Principia, he also explained tides through gravity with great success. He calculated how ocean tides are shaped by the moon's and sun's pull on the Earth, and math lined up with what folks actually saw in tide patterns. But Newton knew his gravity theory wasn't totally complete in explaining everything. Sure, gravity existed and worked through a precise math law, but he couldn't say why it acted the way it did without matter touching matter. This idea of forces working across empty space was hard for many to accept. Critics thought it clashed with the idea that stuff moves stuff by bumping into each other. Some like Descartes and Leibniz argued matter needed to touch to affect anything else. Attraction across space seemed a bit spooky, like going back to old mystical ideas. Newton's supporters found defending this point tricky due to philosophical pushback. Newton argued that just understanding how gravity works through math should satisfy natural philosophers. The fact that gravity is real and predictable was enough for him. He suggested that maybe ether pressure or something else was behind it all, but didn't want to go too far without proof. He didn't want to make guesses without evidence, saying he didn't feign hypotheses. The math behind gravity was solid, even if the mechanics weren't clear. The Principia basically kick-started math-based physics as its own field, with its unique set of standards and rules. Before Newton, philosophy about nature was mostly abstract guessing or geometry, without real-world tests. He showed how to build mathematical frameworks rooted in observation and test their predictions. This became the blueprint for all rigorous science after him. His work didn't just change physics, it rippled out into philosophy and broader intellectual thinking. It showed that human intelligence could uncover nature's biggest mysteries. During the Enlightenment, there was a lot of faith in what reason could do, much of it inspired by Newton's amazing achievements. People in many different fields wanted to be like Newton in their own area. Part 6. Chasing the Alchemical Dream. Isaac Newton poured over 1 million words into alchemy and chemical processes, approaching them with the same fervour and meticulousness as his work in optics and math. For years he filled notebooks, copied ancient alchemical texts by hand, and conducted risky experiments in his lab, all to grasp the active principles of substances. Back then, there wasn't a clear line dividing alchemy from chemistry. They were just two ways of exploring how matter behaves and transforms through observation and testing. Alchemy wasn't just about trying to turn lead into gold. It was woven into the practical crafts of metallurgy, medicine and dye-making too. Newton's alchemical projects were his gateway to understanding the subtle forces at play on the tiniest scales of matter. He imagined that particles interacted through invisible attractions and repulsions, much like gravity, but on a different scale. These hidden forces, he thought, might explain chemical reactions that the mechanical philosophy of the time couldn't make sense of. Thinkers like Descartes saw the world as machine parts clicking together, but that didn't explain why certain chemicals seemed to have a special liking for each other. Why could acid eat through some metals, but ignore others, even if they seemed similar? Newton had a hunch about unseen forces manipulating these chemical behaviours, akin to gravitational pull, but working in the realm of chemistry. Alchemy, with its experimental insights, could unlock these mysteries. In his manuscript, Nature's Obvious Laws and Processes in Vegetation, Newton tackled plant growth from an alchemical perspective, proposing that active principles in plants selectively drew necessary particles from their environment. This was a chemical reaction of sorts, where specific elements came together through their natural attractions. Newton even dabbled in the pursuit of the philosopher's stone, aiming to uncover the legendary substance said to transform metals and grant wisdom, not as a gullible fantasy, but as a genuine scientific endeavour of the era. If altering these particle forces could change a substance's nature, maybe transmutation was possible. Alchemists often wrote in cryptic and symbolic language to keep their secrets hidden, believing in an ancient wisdom buried beneath such layers. Newton was convinced these early alchemical texts held real chemical truths, shrouded in mystery. This curiosity also tied to his broader mission of reviving ancient knowledge, known as the Prisca Theologia. True to his secretive nature, Newton kept his alchemical studies hidden his whole life. It wasn't until after his death that people discovered his lab packed with somewhat unconventional tools and notes, revealing an intense, hands-on approach running parallel to his more famous mathematical work. Newton's interest in these so-called active principles also linked closely with his broader scientific theories. He pondered the idea that gravity itself could be seen as an active principle, suggesting that matter might have built-in tendencies beyond mere inertia. These thoughts challenged the prevailing idea that everything could be explained through basic mechanical interactions. In later versions of his work on optics, he wondered openly about whether particles have inherent attractive forces at short ranges. Could these unseen forces be the key to understanding chemical reactions, surface tension, capillary action, and other intriguing behaviours of nature? The forces driving nature at various scales blended both chemistry and physics, grounding them in shared principles. The idea was that nature functions through attractions and repulsions among tiny particles. These forces change with distance, following mathematical principles much like gravity. Forces like chemical reactions, heat, electricity, and magnetism could all be linked to interactions at the particle level. This concept foreshadowed modern physics, where forces got unified through mathematical field theories. Newton's exploration of alchemy was as meticulous as his optical experiments, characterized by precise observation, manipulation of variables, and thorough documentation. He examined alchemical substances with the same attention to detail he applied to studying prisms and lenses. The difference lay in alchemy's enigmatic theories and symbolic language. Some scholars suggest Newton's study of alchemy directly shaped his ideas about gravitational force. The notion that matter carries active principles, learned from chemistry, might have hinted at non-mechanical forces in physics. The philosopher's stone symbolized matter in its most dynamic form, much like gravitation represented an inherent power present in all matter. Yet others highlight the contrast between Newton's public work in physics and his private alchemical endeavours. The Principia, with its reserved mathematical style, lacks any reference to alchemical ideas. Newton intentionally left alchemical thoughts out of his published natural philosophy, keeping a clear line between solid mathematical evidence and uncertain chemical theories. Both views shed light on Newton's intricate intellectual pursuits. His thinking effortlessly moved across mathematical mechanics, optical studies, chemical operations, and theology. He identified links and parallels where future generations saw distinct fields. This unity lived within Newton's mind, even if not apparent in his writings. Newton's alchemical studies remained largely unnoticed until the 20th century, when his manuscripts were discovered, reshaping his scholarly image. This led to a more nuanced understanding of Newton beyond the rational mechanic of the Enlightenment, revealing his simultaneous exploration of nature and the divine. Modern chemistry confirms some of alchemy's insights while dismissing others. While nuclear reactions can achieve transmutation, the philosopher's stone cannot. Chemical reactions certainly involve atomic forces, not just mechanical interactions. Newton's idea of active principles managing matter offered true insight. His meticulous experimental method later influenced chemistry, even if his theoretical framework didn't succeed. Detailed experimentation with precise documentation became standard practice. Chemists pursued quantitative laws of chemical reactions, inspired by Newton's mathematical methods, separating his sound methodology from his flawed theories. Part 7. The Wisdom of the Ancients. Newton was really convinced that ancient civilizations had a deep grasp of the natural world and the divine, knowledge that had been lost or messed up over time. His fascination with the past wasn't just some romantic notion, it was the core of his intellectual quest. For years he delved into ancient writings, comparing mythologies and piecing together what he called prisca theologia. This ancient theology was about original truths that God shared with Noah and the earliest patriarchs. This idea grew out of Renaissance traditions passed on to Newton, which he then reshaped. Earlier scholars like Marsilio Ficino and Giovanni Pico della Mirandola believed that even pagan philosophers held bits of divine understanding. They linked teachings from Plato, Pythagoras, and Hermes Trismegistus to the biblical revelations. Newton took this idea further, making it more rooted in evidence and historical scrutiny. Newton saw the original religion as being made up of two basic rules, later reaffirmed by Christ. Love God wholeheartedly, and love your neighbour as yourself. According to him, this straightforward monotheism started with Noah and trickled down through Abraham, Isaac, Jacob, and Moses to the Israelites. However, other cultures twisted this pure faith into idol worship, though some truths remained. Newton pored over volumes in his work, Theologiae Gentilis, Originis Philosophicae, mapping out how these distortions occurred. Ancient priesthoods turned the worship of one true God into elaborate multi-god systems. Yet hints of original monotheism lingered in some philosophical schools and mystery religions. Newton was especially captivated by the idea that Pythagoras, during his travels in Egypt and Babylon, picked up genuine wisdom. Newton thought the Pythagorean system was full of real natural philosophy, hidden in symbols. Supposedly, Pythagoras taught that Earth moved around a central fire, which was an early nod to the heliocentric view that Copernicus would later champion. Newton believed ancient thinkers knew the real structure of our solar system. He also believed ancient temple designs and showed off a deep understanding of cosmology. For example, Solomon's temple, along with those dedicated to Vesta, used round shapes with central sacred fires. These designs, Newton felt, represented the heliocentric system with the sun as the centre. To Newton, religious rituals and natural philosophy were originally one and the same. Temples were, in a way, blueprints for the universe, helping people understand that the cosmos was God's grand temple. Architectural details held scientific meaning, open to anyone who could decipher the symbols. That's why ancient wisdom seemed so wrapped in cryptic allegories. Newton's Prisca Theologia idea guided his approach to alchemy and natural sciences too. He thought that alchemical writings carried ancient chemical knowledge hidden in dense symbolic language, meant to keep it safe from distortion. By breaking these codes, one might rediscover lost experimental methods and theories. Newton wasn't just discovering, he was rediscovering what the ancients already knew. To him, his work was about restoring lost knowledge rather than breaking new ground. He hoped to bring back Prisca Sapientia, that ancient wisdom bridging natural and divine realms. He believed modern philosophy had fallen short of the heights reached by ancient masters and needed a fresh start. His Principia was an attempt to revive the mathematical natural philosophy that Pythagoras had held. In his chronology studies, Newton tried to pin down accurate timelines for ancient history using astronomical clues. Ancient records often mention celestial events like eclipses and planetary alignments. By pinpointing when these cosmic happenings took place, Newton aimed to precisely date historical timelines, revealing the real progression of ancient cultures and exchanges. Newton challenged the accepted dating of Egyptian and Greek history, suggesting they weren't as old as traditionally thought. By correcting these timelines, he showed that all ancient wisdom ultimately traced back to biblical patriarchs. His work reaffirmed the primacy of Hebrew revelations over supposedly ancient pagan traditions. Newton dived deep into exploring mythological traditions across various cultures, examining their common roots. He mapped out how the same core tales resurfaced in Greek, Egyptian, and Near Eastern myths, albeit with some variations. These similarities hinted at a single source that each culture adapted. By comparing mythology, Newton uncovered historical links between ancient peoples and their way of sharing knowledge. He was convinced that Phoenician sailors spread ancient wisdom along the trade routes connecting different civilizations, passing on astronomical insights, religious beliefs, and philosophical ideas throughout the Mediterranean region. This helped explain why some distant cultures shared similarities, despite having no apparent direct contact. Ancient globalization, it seemed, happened through these trade connections. Newton also delved into the secretive world of ancient mystery religions, exploring how they safeguarded knowledge through initiation rites. The Eleusinian mysteries and similar groups kept these truths hidden from the public, revealing them gradually to initiates over time. This system of hierarchical knowledge ensured that traditions remained untarnished. Newton's habit of keeping important ideas to himself was inspired by this old practice. He thought that deep truths shouldn't be shared with those not ready to truly understand them. By following the Pythagorean method of embedding deeper meanings in straightforward comments, Newton found his own way. He crafted the general scholium for readers who could dig deeper beneath the surface. This let his work speak to different audiences on multiple levels. Everyday readers discovered mathematical proofs and experiments, while those in the know saw theological links and connections to ancient wisdom. Newton skillfully communicated with many through intentional ambiguity. His Prisca Theologia framework tied his natural philosophy closely to his anti-Trinitarian beliefs. According to him, pure monotheism was the original religion before being modelled with Trinitarian beliefs in the 4th century. Similarly, the earliest natural philosophy recognised mathematical laws in a heliocentric cosmos, which later fell out of favour. Newton aimed to restore both religion and science to their original purity through thorough scholarship and empirical work. He believed he was living in a time of predicted restoration, inching closer to completion. While the Protestant Reformation had begun reviving true religion, it was still unfinished. Newton saw his contributions in natural philosophy as a part of a larger movement to restore ancient wisdom. Both science and theology, in his view, were key parts of God's plan to reveal the truth to humanity. Newton didn't see himself as a revolutionary breaking from tradition, but as a restorer of lost knowledge. His mission was to recover and refine this ancient wisdom for future generations. Modern scholars debate how much weight to give to Newton's Prisca Theologia framework. Some see it as a minor hobby unrelated to his scientific work, while others argue it was central to his motivation and methods. Evidence suggests it was indeed crucial to how Newton saw himself and his intellectual purpose. This framework also mirrored broader cultural beliefs of his time regarding knowledge and history. Many 17th century thinkers thought human learning had declined since ancient times, and that progress meant recovering lost wisdom rather than uncovering new truths. Newton's Prisca Theologia fit comfortably within these views, yet he pursued these ideas with greater intensity and discipline than his peers. His calculations and mythological comparisons ventured far beyond casual interest. For Newton, reconstructing ancient wisdom traditions was a major endeavour, not just a side interest. Part 8. Impact and Legacy. Newton's ideas changed philosophy as drastically as they shook up physics and math. Every big thinker during the Enlightenment in the 1700s had to deal with the fallout of his work. His approach, his views on the universe, and his math accomplishments set the stage for 18th century philosophy. To understand this era, you've got to see Newton's philosophical impact, not just his scientific feats. John Locke was personally acquainted with Newton, and they both shaped each other's philosophical views a lot. Locke's belief in empiricism put the focus on sensory experience as the basis of knowledge, pushing aside Descartes' idea of inborn concepts. This meshed well with Newton's hands-on approach and skepticism about purely rational metaphysics. Both were adamant that theory should be firmly rooted in the careful observation. Yet Locke also noted the limitations of what sensory experience alone could tell us about nature. He separated primary qualities, like size and motion, from secondary qualities, such as colour and taste. Primary qualities belong to objects themselves, but secondary ones rely on perception. This was an attempt to bring mathematical science and empiricist views together. Newton influenced Locke's thoughts on space, substance, and understanding reality. Locke struggled with whether space was a substance, a property, or just a relationship. Newton's idea of absolute space provided one answer, although Locke never fully bought into it. Their exchange showcased their ongoing conversations about deep metaphysical and knowledge-based issues. George Berkeley came up with an idealist philosophy, partly responding to Newton's mechanics and Locke's empiricism. Berkeley tossed out the concept of material substance, arguing that only thoughts and ideas exist. He believed physical objects were just collections of sensory ideas perceived by minds. This bold move aimed to close the gap between appearance and reality that bothered Locke. Berkeley also criticised Newton's absolute space in calculus on both philosophical and math grounds. He said that space existing outside our perception made no practical sense. He thought the calculus's reliance on the fuzzy idea of infinite symbols that were neither something nor nothing just didn't add up. These critiques highlighted real issues in Newton's foundations, though his system remained successful. David Hume tried the most thorough application of Newtonian methods to human nature and ethics. His book, A Treatise of Human Nature, aimed to bring the experimental method to moral issues, hoping to achieve in psychology and ethics what Newton did in physics. This meant finding patterns in human thought and behaviours and coming up with general principles to explain them. Hume's exploration of causation directly interacted with Newton's methods and their philosophical underpinnings. Newton claimed to derive the existence of gravity from observations using induction. But Hume argued induction itself has no solid rational backing beyond habit and tradition. We can't prove that unobserved cases will match the observed ones. To Hume, causation simply boiled down to the regular sequence of events in our experience. We notice certain events tend to follow others and form expectations based on that. But we never directly see any necessary link between causes and effects. The idea of causal power is more of a mental projection than an empirical finding. This skeptical perspective posed a philosophical threat to the Newtonian framework. If induction lacks a rational base, then Newton's conclusions from observations can't be justified. The laws of motion and gravity become as uncertain as our usual expectations. Hume's thought stirred up what Kant later called a crisis waking him from dogmatic slumbers. Despite this, Hume was impressed by Newton's accomplishments and didn't mean to undermine them. He differentiated between practical certainty that suits life and science versus true philosophical certainty. Newton's approach was effective, even if its ultimate justification was philosophically uncertain. We can use induction with confidence, while admitting we can't completely explain its success. Continental thinkers interacted with Newton's ideas in their own way, different from the British empiricists. Voltaire became one of the most enthusiastic promoters of Newton's ideas in France during the 1730s and 40s. He wrote elements of Newton's philosophy to make the Principia and optics more accessible to educated folks who weren't experts in mathematics. In Voltaire's view, Newton was a role model for the power of reason, opposing religious superstition and rigid philosophical ideas. A woman named Émilie du Châtelet created the ultimate French version of the Principia, still in use today. An exceptional mathematician, she had a deep grasp of Newton's work, both technically and philosophically. Her notes made tricky parts clearer, linking Newtonian physics to Leibnizian metaphysics. Châtelet demonstrated how to blend insights from clashing philosophical schools. The Leibniz-Clark correspondence from 1715 to 1716 became crucial for later philosophical discussions. Leibniz criticized Newton's idea of absolute space, arguing it went against the principle of sufficient reason. Samuel Clarke defended Newton, discussing how space relates to God's omnipresence and actions. This exchange highlighted fundamental differences between rationalist and empiricist viewpoints. Such debates were essential throughout the 18th century, impacting thinkers across Europe and influencing Kant in the 1770s as he struggled with concepts of space, time, and causation. Kant noticed flaws in both rationalist metaphysics and empiricist skepticism, as neither could fully explain how Newtonian science achieved knowledge about nature. His critical philosophy tried to move beyond the rationalist-empiricist divide that Newton's work embodied. Kant viewed space and time as neither objective realities nor just empirical relationships, but as forms that shape our experience. This meant they were necessary but not independent of human thought. He argued Newton's laws held true because they reflected how we must structure experience. Causation, Kant said, isn't found through observation like Hume suggested or reasoned from pure logic as rationalists claimed. Instead, it's a concept our minds use to make sense of things, allowing for objective experiences. This perspective explained Newton's success and the limits of what physics can uncover about the ultimate nature of reality. Kant's reinterpretation influenced German philosophy during the 19th century, separating Newton's physics from his beliefs in absolute space and divine intervention. The laws could be kept while discarding Newton's theological and metaphysical views, supporting the secular scientific outlook of the 1800s. Meanwhile, science advanced by expanding Newton's methods into new areas. Lagrange and Laplace developed analytical mechanics, using new math techniques to reformulate Newtonian physics. They successfully predicted planetary movement with amazing accuracy. Laplace famously claimed his celestial mechanics worked without any need for God's involvement. This turn of events flipped Newton's original intentions, as he saw physics as a way to understand divine action. The Enlightenment rebranded Newton as the symbol of rational, secular inquiry, often ignoring his theology, alchemy, and interest in prophecy to focus solely on his mathematical physics. This version of Newton became more a mythical icon than an accurate historical figure. In the 19th century, Newton's mechanics were applied to areas like electromagnetism, thermodynamics, and statistical physics. Maxwell's equations for electromagnetic fields followed Newton's method of using math to generalize from experiments. The kinetic theory of gases used Newtonian mechanics to explain molecular motion and thermodynamics. Successful physical theories adopted Newton's framework, blending math with empirical evidence. Yet some anomalies couldn't be explained by Newtonian physics. Mercury's orbit didn't match gravitational predictions. The speed of light seemed constant in all reference frames, contradicting Newtonian relativity. Atomic phenomena required discrete energy levels, conflicting with classical mechanics. Then Einstein's relativity theories in 1905 and 1915 fundamentally changed the game, shifting away from Newtonian mechanics. Space and time aren't fixed. They change depending on the observer's point of view and merge into what's known as space-time. Gravity isn't a force, instead it's a bending of space-time caused by mass and energy. These ideas shake up Newton's basic ideas, though they still keep his laws as reliable estimates. Then in the 1920s, quantum mechanics took a further step by challenging Newtonian certainty in a big way. At tiny scales, physical processes include true randomness, rather than just a lack of knowledge of starting points. Particles don't have precise locations and speeds at the same time, which goes against classical views. The math behind quantum theory looks nothing like Newton's mechanics, but despite these huge shifts, Newton's wider approach to science held on. Physics still mixes math theory and experimental tests, much like Newton did. We frame laws as differential equations to set limits on potential behaviors. Theories thrive by making very accurate predictions that we can either confirm or disprove through observation. Philosophy of science keeps chewing over questions that sprang from Newton's work, like how observations guide which theory gets picked when several could explain the same data, or what makes a scientific idea valid compared to speculative metaphysics. Newton's hypotheses, non-fingo idea, is still relevant today when discussing scientific realism and methodology debates. Part 9. The tensions and limits. Newton's ideas had some deep contradictions he never really solved, and later scientific developments brought them to light. While Newton claimed he drew conclusions from observable phenomena without making up hypotheses, his whole approach leaned heavily on metaphysical ideas like absolute space, which nobody can actually see. From the start, critics were uneasy about this disconnect between what he said about empiricism and what he actually did, which was more rationalist. For Newton's physics to work, the concept of absolute space was crucial. The laws of motion need a way to tell real acceleration, apart from just shifts in relative position. Without the concept of absolute motion, his second law would mean nothing, as all motion is merely relative to a chosen reference frame. Yet Newton himself admitted that you can't directly measure absolute space and time. He tried a workaround by suggesting that forces give us a way to observe true acceleration. According to him, actual changes in motion are due to forces acting on objects, which we can detect through visible signs like the water's behavior in a spinning bucket. But this argument has a flaw. It assumes you already know how to distinguish real motion from apparent motion before identifying forces. The famous bucket experiment was meant to prove absolute rotation separately from other reference objects. When the bucket spins, the water inside eventually spins too, forming a concave shape. Newton argued this showed true rotation since the water's shape changes, even when it moves with the bucket, implying the rotation is relative to space itself, not nearby objects. In the late 1800s, Ernst Mach questioned this logic, suggesting other interpretations. Maybe the water's shape changes due to its rotation in relation to distant stars in the universe. If the stars instead rotated around a stationary bucket, the same thing might happen. This challenged Newton's claim of demonstrating absolute motion. Later, Einstein's theory of general relativity supported Mach's ideas, showing that inertial effects rely on how matter is spread out. Mass shapes space-time, which then defines local inertial frames. The separation between inertial and non-inertial motion holds, but is dynamic, not absolute. Space isn't independent with a fixed structure deciding acceleration. Newton's gravity theory also faced a big issue with the concept of action at a distance, as pointed out by followers of Cartesian and Leibnizian ideas. How could the sun pull on Earth from 93 million miles away without any physical contact? Mechanical philosophy demanded direct contact for causal effects, and gravity seemed to break this rule, bringing back ideas medieval philosophy had already set aside. Newton understood this problem, but insisted that proving gravity's existence and its laws through math was more important than fulfilling mechanical expectations. He even speculated privately about an ether that might mechanically transmit gravity, but chose not to publish such ideas because they lacked experimental proof. His brave philosophical stance meant accepting the unknown rather than making up explanations. This left him open to criticisms of inconsistency, since he asked others for mechanical reasons, while sparing his gravitational force from needing one. Leibniz and Huygens argued that vortex theories at least attempted to propose mechanisms, even if they were speculative. Newton's stance seemed to abandon the quest for true physical explanations altogether. Eventually, physics proved Newton's willingness to accept mathematically defined forces without needing mechanical reduction was correct. Electromagnetic forces similarly act through empty space without any material connection. Quantum field theory describes forces using field equations instead of physical particle interactions. Seeking mechanical explanations turned out too limiting for fundamental physics. Yet unlike Newton's gravity, these modern forces propagate at finite speed rather than instantaneously across any distance. When source masses change, their effects on faraway objects take time to travel at light speed through space-time. Newton's concept of instantaneous action at a distance was not just unexplained, it was factually incorrect. The particle theory of light highlights another big flaw in Newton's physics. He put forth strong arguments suggesting light is made of particles rather than waves. Light moves in straight lines and casts sharp shadows, unlike sound, which bends around obstacles. Reflecting light is like elastic particle collisions off surfaces. But Newton's idea couldn't fully explain things like the colours in thin films. Why does light sometimes bounce off soap bubbles and other times pass through them unpredictably? Newton suggested that corpuscles were alternately inclined to reflect or transmit. These fits awkwardly mixed wave properties with a particle basis. Then in 1801, Young's double-slit experiment dealt a huge blow to the particle theory. The interference patterns of alternating bright and dark stripes clearly showed wave behavior. Particles going through two slits couldn't create those patterns. By the mid-1800s, the wave theory had taken over optics. However, around 1900, the discovery of the photoelectric effect brought the particle concept back into play unexpectedly. Light knocks electrons off metals in a way that wave theory can't properly account for. Einstein demonstrated that treating light as small packets of energy made the observations fit perfectly. The modern idea of photons confirmed some of Newton's insights, even if his theory was wrong. Ultimately, wave-particle duality surpassed both viewpoints, showing that neither particles nor waves fully capture what quantum objects are like. Light shows both wave and particle traits, depending on the experiment. Newton and Huygens each got part of the picture right, but were fundamentally mistaken. Nature's ways at the quantum level defy classical ideas altogether. Newton's methods created a tension between cautious observation and daring theory. He claimed to draw conclusions from observations using induction, shunning speculation. Yet his concept of universal gravitation went far beyond direct evidence in bold theoretical moves. He only tested on Earth and with visible celestial bodies. Extending this to all the matter in infinite space was a huge theoretical gamble. There could be countless unknown exceptions beyond what he could test. Newton's Rule 3 justified this sweeping generalization, but that rule wasn't drawn from observations. It was a methodological principle needed for natural philosophy. David Hume's critique of induction exposed this vulnerability. No amount of consistent observation proves future cases must be the same. You can't show induction is valid by using induction itself, since it would just go in circles. Newton's bold assumptions, based on limited data, lacked the certainty he claimed. The problem of induction is philosophically unresolved, even if science thrives on it practically. We keep using inductive reasoning because it works, not because we can justify it perfectly. Newton's method worked incredibly well, but its logic was shaky. This gap between practical success and philosophical grounding is still in science today. Newton's religious views also clashed with his public science stance. He believed God actively maintained cosmic order through direct intervention, but his published works portrayed nature as governed by mechanical mathematical laws. The relationship between divine action and natural law stayed unclear. If God has to tweak planetary orbits, then natural laws aren't self-sufficient. Leibniz argued that such a view implies an imperfect world needing divine fixes. On the other hand, if laws are enough, then God's role is limited to creation, as deists thought. Newton wished for God's active role without undermining the self-governing nature of laws. His heretical religious views added more complexity, which he hid from the public. The general scholium hints at Arian theology visible only to those aware of these debates. Newton managed both to make physics accessible to the public, while embedding hidden heretical religious beliefs for the initiated. This double practice reflects his struggle between intellectual honesty and the need to survive. Newton's theological and alchemical writings got pushed into the background, leaving a skewed image of his legacy. Enlightenment thinkers hailed him as the epitome of pure, rational science with no religious bias. But in reality, Newton spent more time on theology and alchemy than on physics. His all-encompassing vision of blending these fields ended up split into conflicting parts. While modern physics has let go of many of Newton's original theories, it holds on to his methodological insights. Concepts like absolute space and time have been replaced by relativistic space-time. Gravitational force, now it's space-time curvature. Deterministic paths gave way to the probabilities found in quantum mechanics. Yet the mathematical physics Newton introduced remains the backbone of modern physical science. The belief that nature operates under precise mathematical rules is still key, even with all the shifts in theory. Today's scientific process of making predictions and testing them roots back to Newton, even though his theories had their limitations. Part 10. The Big Picture. To truly understand Newton, you need to see how his seemingly disconnected interests all came together as one big picture in his mind. There were no strict lines dividing subjects like physics, theology, alchemy, and history for him. He saw all these studies as different paths to uncovering God's nature and intentions through the world around us. Natural philosophy, biblical analysis, and alchemical experiments were just different ways to chase the same ultimate truth. Newton thought of God as having left clues about divine wisdom in many books, each needing its own way to be read. In the book of nature, you find God's power and intelligence through math and the orderly way the world works. The book of Scripture shows God's plans for humanity through its stories and prophecies. Ancient philosophical and alchemical writings hold broken bits of ancient revelations, When you look at them the right way, all three sources point to the same truths. Natural philosophy uncovers the math that rules motion and forces. Theology digs out pure monotheism beneath the layers of Trinitarian beliefs. And through alchemy, you grasp the active principles that govern the transformation of matters beyond just mechanical beginnings. The idea of prisca sapientia ties it all together, showing these areas all stem from the same divine revelation. Newton thought God had revealed these natural and moral truths to Noah and the patriarchs, with their descendants passing down this wisdom, albeit imperfectly. For him, the job was to clean up and bring these traditions back to their original unified knowledge form. His push against the Trinity wasn't just a side thing, it was a huge part of his entire vision. For him, the Trinity was as corrupt as the medieval misunderstanding of natural philosophy. Just as scholastic Aristotelian views messed up the true laws of nature, Trinitarian ideas clouded the clear monotheistic truth. Both needed a reboot by going back to the roots and stripping away the added-on stuff. Newton's view of God being completely one and everywhere played an essential role in shaping his physics. Since God is everywhere, he's the very fabric of space thanks to his eternal presence. That made space more a divine quality than just a dimensional arena. Space's unity and unbroken nature mirror God's undivided nature. Time, with its absolute flow, shows off God's endless existence, organizing everything that happens. God sees the past, present and future all at once, while we live time moment by moment, moving forward with no turning back. This absolute time is the backdrop for all change and motion. Gravity, Newton guessed, might even be God's direct action, not simply a force spreading through matter. God holds the universe in place by pulling all objects toward each other. The inverse square law in math explains the way God manages the movement of the planets. What we call natural law is really God's will acting in a steady, predictable way. Newton had faith in the universality of mathematical laws, trusting that God's rational and steady nature would make sure divine actions were consistent everywhere. The same laws held across the endless stretch of space, because one God governs it all. In doing so, mathematical natural philosophy becomes a peek into God's rational nature stamped onto our world. Newton turned to alchemy to find the active principles that could fill in the gaps left by pure mechanics, which thought of matter as just passive and lifeless. Pure mechanics couldn't account for things like chemical reactions or life processes. In contrast, matter guided by active principles could combine selectively in ways pure mechanics couldn't achieve. These principles might be God's creative acts at an unimaginably small level. The philosopher's stone stood for matter at its most energized and perfected, loaded with divine virtues. Changing base metals into noble ones became conceivable by adding these active principles, altering their fundamental nature. This wasn't about magic, but taking natural inquiry to places where simple mechanics fell short. Alchemy explored divine interactions with matter, adding depth to mathematical physics. Newton's work on biblical prophecy also fit into this grand scheme. It was all about unlocking God's plan for how history would unfold. Daniel and Revelation provided clues about the timeline of how true religion got corrupted and how it would eventually be restored. Figuring out these prophecies helped pinpoint humanity's place in God's plan. Newton figured he was living during a long period of predicted decline before a final reform. His work on timelines was precise, showing how ancient wisdoms developed and mixed. He wasn't just curious about the past for the sake of it, but wanted to understand how knowledge was passed down. By tracing how Egyptians, Greeks and Hebrews exchanged and altered original revelations, he identified which traditions kept the true faith. History showed the decay Newton wanted to fix with his restoration effort. The core idea in all these projects was careful observation and analysing texts. Whether he was looking at light through prisms, poring over old books, or doing chemical tests, Newton was all about detailed empirical methods. He critically assessed evidence, compared various sources methodically, and made cautious conclusions. This same approach guided both his science work and biblical studies. Newton's approach in physics spilled over into his theological studies, treating scripture almost like scientific data. He closely compared different versions of texts, spotted differences in later editions, much like how a scientist classifies specimens. His text analysis identified corruptions and separated true revelations from human edits. This method of approaching theology upset those who saw the scriptures as 100% divine. Similarly, in alchemy, he wasn't just going to accept old ideas without testing them. He did thorough experiments, noting results and tweaking his approaches based on what he observed. His experimental mindset unified his work in areas others viewed as unrelated. For Newton, any kind of knowledge needed to be backed by evidence, no matter the field. Math was also a key part of Newton's wide interests, though it's not as obvious as his experimental methods. He used math openly in explaining motion and gravity, but he also used it for figuring out historical dates based on stars. Even interpreting prophecies involved numbers and calculations. Newton saw math as mirroring God's rational design of the universe. The mathematical harmony seen in how planets move showcases God's perfect order and beauty. Ancient thinkers saw this too, which is why Pythagoras stressed math in his philosophy. Math offered a special window into divine wisdom, underlining everything. This unified way of seeing things explained Newton's incredible drive and achievements across various fields. He wasn't just dabbling in different hobbies, but was focused on one huge goal with his everything. Every study he did was about learning more about God and bringing back original divine wisdom. This work was crucial to him, far beyond simple curiosity. It also explains why he kept much of his work secret. Controversial theology could ruin his mission. Publishing unfinished alchemy ideas might open sacred knowledge up to ridicule or distortion. So Newton held back what he thought wasn't ready for the public, while putting out what could help the general understanding. Sadly, this full vision didn't last after Newton's time. Those managing his papers kept back his theological and alchemical writings to protect his legacy. The Enlightenment painted Newton as a rationalist, leaving out the theology that truly drove him. The clean-cut image of Newton didn't match the real person. Modern scholars have carefully pieced together his unified vision from his manuscripts. We now see that physics, theology, and alchemy were all interconnected in Newton's mind. This changes how we read his known works, revealing deep layers of meaning we didn't see before. The theological mentions in his general scholium aren't side notes but key beliefs, fuel the entire Principia. We can't completely grasp Newton's viewpoint because our intellectual scene today is a world apart from his. We see science and religion as separate spheres with no overlap, and we draw a much firmer line between empirical inquiry and metaphysical reflection compared to Newton. Our tendency to compartmentalize fields of study obscures the links Newton found obvious. His integrated vision came with real tensions and contradictions that he couldn't fully untangle. The question of how divine intervention meshed with natural laws was tricky. Was matter imbued with active properties on its own, or did it strictly depend on divine intent? The connection between mathematical descriptions and physical explanations was a source of ongoing puzzlement. These challenges triggered productive debates, pushing later thinkers to confront basic issues about how we explain things scientifically. Is the role of physics just to mathematically describe how nature acts, or to also explain why it acts that way? Can we divorce empirical science from deeper metaphysical assumptions about reality's essence? Newton's work brought these questions to the forefront, necessitating a philosophical discussion. His influence extends beyond just science. It shapes our entire notion of inquiry. The mathematical physics domain Newton pioneered became the blueprint for all precise sciences, but the philosophical dilemmas his work highlighted continue to fuel discussions on scientific methods and realism today. We still grapple with some of the puzzles Newton posed, even as we've moved past his specific answers. Seeing Newton in full Combining his public work in physics with his private pursuits in theology and alchemy reveals a mind of incredible breadth and depth. He was a master of mathematics, physics, astronomy, optics, theology, history, chronology, and chemistry. What's more, he perceived deep connections across these fields where others saw only divisions. This comprehensive vision drove all his accomplishments. The cohesive version of Newton challenges our beliefs about how great thinkers operate and what fuels scientific breakthroughs. We often think of scientific inquiry as detached from religious and metaphysical ties, yet Newton's story shows a far more nuanced reality, one where religious beliefs and scientific methods are entwined. His unorthodox religious views and alchemical research weren't roadblocks to his scientific work. Rather, they were integral to his broader search for truth.